Welcome to today's paper reading. Today's paper is titled, ADen, Adaptive Density Representations for Sparse-view Camera Pose Estimation. This paper was published on AR14 by Tang and colleagues from FAIR at Meta. Camera pose recovery is a fundamental task in 3D computer vision, crucial for applications like 3D scene and object reconstruction. Traditional methods rely on feature correspondence, which requires significant overlap and minimal viewpoint changes, posing challenges in sparse-view scenarios. Recent data-driven approaches have aimed to directly output camera poses, either through regression or probabilistic modeling. However, these methods face limitations, such as being ill-posed in the presence of symmetry or requiring high computational resources. In this paper, the authors propose ADen, which unifies a generator and a discriminator to handle multimode ambiguity and improve both precision and runtime, outperforming previous methods in empirical evaluations. The recovery of 3D structure from sparse-view images is crucial in computer vision. Recent advancements in neural radiance field, NeRF, and Gaussian splatting have enabled high-quality 3D reconstruction and novel view synthesis. At the core of these methods, structure from motion, SFM, is essential for extracting camera poses from input images. However, challenges arise in sparse-view scenarios where minimal view overlap can cause traditional SFM pipelines to fail. This necessitates the need for sparse pose estimations, leading to the development of data-driven approaches that outperform geometric-based methods. These approaches can be broadly categorized into direct regression of 6D camera parameters and modeling rotation as a probability distribution, both of which face challenges in sparse-view settings, particularly with symmetric objects or scenes. Figure 1 illustrates the ambiguity in wide baseline images, focusing on the differences in handling rotation ambiguity between implicit PDF/rel pose and ADen. Implicit PDF/rel pose models rotation as a probability distribution using an energy-based method, necessitating the evaluation of densely sampled rotation hypotheses. For high accuracy, rel pose assesses 500,000 rotations for each image pair, leading to significant computational costs. Conversely, ADen directly outputs 500 high-accuracy hypotheses, circumventing the constraints imposed by grid resolution. The filled circles represent samples, while the unfilled circles denote the ground truth relative rotation. This comparison highlights ADen's efficiency and effectiveness in handling rotation ambiguity compared to rel pose. The related work can be categorized into three main areas. First, structure from motion, SFM, aims to recover 3D geometry and camera poses from multi-view images. This involves computing image features, establishing feature correspondence, and verifying epipolar geometry. Second, data-driven pose estimation methods use neural networks to directly estimate camera poses from images, addressing challenges like symmetry and sparse views. Finally, generative learning models the pose distribution using techniques similar to GNs, with a focus on applying contrastive laws to score samples from the distribution. Figure 2 provides an overview of ADen, a novel method designed for recovering camera poses from sparse-view RGB images. The process begins with the extraction of per-image features using the ResNet backbone. These features are then fused globally using a transformer, which allows for the propagation of information across all images. ADen predicts a non-uniform distribution of camera poses for each image by first applying a pose generator head to the fused features, producing a support set of M camera poses. Subsequently, a pose discriminator, also utilizing the fused features, predicts the probability for each generated pose. This dual approach ensures a comprehensive and accurate recovery of camera poses, even in sparse-view scenarios. ADen's method focuses on recovering camera extrinsics from a set of n sparse-view images. The objective is to determine the rotation and translation for each image. The model architecture includes a shared feature backbone, a pose generator, and a pose discriminator. During training, the method aims to prevent mode collapse by using a geodesic distance loss for rotation and an L2 loss for translation. Additionally, a contrastive loss is employed to differentiate ground truth poses from generated hypotheses. Table 5 presents an ablation study on the training strategies for the generator and discriminator in the ADen model. The study highlights that applying regression loss only to the nearest few samples during generator training allows the model to explore alternative modes, thereby improving performance. Furthermore, training the discriminator with generated noisy camera poses achieves a balance between accuracy and training efficiency. These findings underscore the importance of flexible training strategies to enhance the model's ability to handle multimodal distributions and improve overall performance. In this section, we discuss the experimental setup and results. We used the CO3DV2 dataset, which includes 51 object-centric sequences, for training and testing ADen. Additionally, we evaluated ADen on the Objectron and Niantic map-free relocalization datasets in a zero-shot setting. For evaluation, we focused on rotation accuracy, measuring errors less than 15 degrees, 5 degrees, and 10 degrees, and translation accuracy within 10% of the scene scale. Our method, ADen, consistently outperformed state-of-the-art methods across different metrics and datasets, demonstrating significant improvements at tighter error thresholds and strong generalization capabilities. Figure 3 illustrates the camera pose prediction capabilities of the ADen model when applied to CO3D examples. The figure highlights the training process of the generator, which directly influences the quality of the generated sample distribution and, consequently, the model's performance. By default, the model only applies LG to the camera pose closest to the ground truth, allowing it to move samples closer to the ground truth while enabling other samples to explore different modes without penalty. The figure compares the results of training the generator by pulling 2%, 10%, and all samples towards the ground truth, demonstrating the varying impacts on the camera pose prediction accuracy. Figure 4 illustrates the relative rotation predictions made by ADen in ambiguous cases. Each filled circle size corresponds to the probability assigned by the discriminator, indicating the confidence level of the prediction. The unfilled larger circle represents the ground truth, providing a reference for comparison with the predicted rotations. Figure 5 illustrates the performance of the generator and discriminator in relation to the number of sampled poses. The figure highlights that ADen, which uses a generator to produce samples, significantly outperforms RelPose++, which relies on random sampling from the SO3 sphere. Specifically, ADen achieves higher rotation accuracy with just a few hundred samples, as shown in Figure 5a, surpassing the accuracy of RelPose++ with 500,000 rotations. Figure 5b further demonstrates the generator's performance by measuring the error of the rotation hypothesis closest to the ground truth. This analysis shows that the generator can achieve similar accuracy to dense sampling from SO3, with only 500 samples, emphasizing the efficiency and effectiveness of the generator in producing accurate poses. Figure 6 provides a visualization of the generator's output, highlighting the distinction between ground truth rotations and generated samples. Unfilled circles in the figure represent the ground truth rotation, while dots signify the rotation samples generated by the model. The figure includes examples of more challenging cases, such as those involving symmetry, where the generator effectively models the distribution of rotations, as seen in the donut and wine glass examples. This visualization underscores the generator's ability to handle complex scenarios while maintaining accuracy in its predictions. Table 1 presents the pairwise relative rotation accuracy at 15 degrees, showcasing the performance of ADen in comparison to state-of-the-art SOTA methods. The table measures the relative angular errors between the predicted and ground truth rotations, reporting the accuracy as the proportion of errors that are less than 15 degrees. ADen consistently demonstrates superior performance across different numbers of input images, highlighting its effectiveness in achieving higher accuracy in rotation estimation tasks. Table 2 presents the pairwise relative rotation accuracy at 5 degrees and 10 degrees, denoted as ACC at 5 and ACC at 10, for ADen, PoseDiff, and RelPose++. The table highlights that ADen's performance is not limited by the accuracy of the sampled grid on the SO3 space, which allows it to achieve significant improvements at more stringent accuracy thresholds. This underscores ADen's ability to generate samples that closely match the ground truth camera pose, especially in scenarios requiring high precision. Table 3 presents the translation accuracy of camera predictions, specifically focusing on the proportion of translations that fall within 20% of the scene scale for each sequence. This table compares the performance of ADen against several baseline methods, including CallMap, pose regression, and RelPose++. The data is organized to show how the accuracy varies with different numbers of input images, highlighting ADen's superior performance in maintaining precise camera translation estimates across various scenarios. Table 4 presents the results of a zero-shot evaluation conducted on 2 additional datasets, Objectron and Niantic map-free relocalization. The evaluation focuses on the accuracy of rotation predictions within 15 degrees and camera center predictions within 20% of the scene scale. The table compares the performance of different methods, including MediaPipe, PoseDiff, RelPose++, and our proposed method. The results highlight the accuracy of each method across varying numbers of images and camera center distances, providing insights into the effectiveness of each approach in zero-shot scenarios. Table 6 presents a comparison of inference speeds among various methods, with ADen demonstrating a significantly faster performance. ADen achieves an average speed of 20 fps when processing 9 images, outperforming other methods such as Sparse-pose at 3.6 fps and RelPose/RelPose++ at 48 fps. This table highlights ADen's efficiency and effectiveness in real-time applications, underscoring its superiority in both speed and accuracy. In this paper, a new learning-based method is introduced for recovering camera poses from Sparse-view RGB images. The ADen network, featuring a pose generator and a pose discriminator, effectively navigates the ambiguity in wide baseline images. Experimental results show that ADen achieves state-of-the-art performance on the CO3D dataset, particularly excelling in accuracy at lower rotation error thresholds. Additionally, ADen's efficient generator allows for real-time inference of poses from multiple images, significantly improving speed over previous methods. Thank you for watching.